right, everyone. I am here with Stefano Soatto. Stefano is VP of AI Application Science at AWS, as well as a professor of computer science at UCLA. Stefano, welcome to the TWiML AI podcast.
Thanks for having me.
I'm really looking forward to digging into this conversation. We'll be talking about some of your recent work on an area you called Graceful AI, which is very interesting. But before we do that, I'd love to have you share a little bit about your background and how you came to work in machine learning.
Yeah, I appreciate that. My background is a bit unusual. I grew up in Italy, as you can tell from my accent. And I grew up studying classics like history, philosophy, Latin, Greek, and so on and so forth. And before going to college, I entered a context for a summer course organized by a tiny school that has a class of letters and a class of science. And I was there to study philosophy, but I realized that there were problems that people were writing on a board that I had no clue how to solve. And these were math problems. And it really, really bugged me. And so I got more and more interested in that side, and I started attending those seminars. And then I enrolled in engineering. And in 1989, I ran across the work of Ernst Dickmanns. Ernst Dickmanns was a pioneer of autonomous driving back in 1989 in Germany. He was the one that had autonomous vehicle going on the Autobahn at speeds up to 180 kilometers per hour. And when I joined Caltech for my PhD, I was in a department of control and dynamical systems. And that's where I got exposed to computer vision, because the reason we don't have domestic robot helpers is not because we don't know how to control them, because we don't know how to endow them with a representation of the surrounding world. And so I got more and more interested in that problem. And that was a quarter of a century ago, and I'm still very excited and interested about that area. And so that's how I got into AI.
Nice. We could spend a whole different interview talking about that. One of my perennial favorite topics is the relationship between kind of control and machine learning and end-to-end systems versus more modular systems that use what we've learned about physics and control and other things. But I think that's going to be a different conversation. Tell us a little bit about your both your role at AWS as well as your research interests across AWS and UCLA.
Yeah. So at AWS, I'm in charge of the science for AI applications. And AI applications are grouped by modality. So we have vision, so audio, images and video. And then we have speech, and then we have text, and then we have vertical. And verticals are domain-specific applications in the industrial space, as well as operations and time series, forecasting, and so on and so forth. Mm-hmm. And we are organized as research teams, but we are very closely coupled with engineering teams, product teams, and data teams. And we practice what we call customer-obsessed science, which is different than curiosity-driven science, which is what we do at the university. And so our work ends up in the hands of customers in a time frame that is quite fast for somebody who's used to academic time clock, where you expect your impact in the world to be posthumous, or if you're lucky, during your lifetime. But here, there's a very quick turnaround between ideas being generated, services being deployed, and customers using them and getting benefit from it. So my interest is, broadly speaking, in AI. I've always been interested in autonomous systems that interact intelligently with the environment, where intelligent is to be defined. Everybody has their own. But to me, a dog is plenty intelligent. I wish we could build something that behaves like a dog. So that's much more difficult than doing a chess-playing program. In a fight for survival, the dog will win over the chess-playing program anytime. So it just needs to unplug the power. And definitely there are opportunities that the time is right for research that we've been doing for 10, 20 years to become useful now. And for me, the game changer was in 2009, I read a report by Cisco called Visual Networking Index that kind of pointed out that back then, 2009, peer-to-peer traffic was surpassed by video traffic on the internet. And they were forecasting that by 2022, it would be 90% of wireless traffic and almost the totality of internet traffic. And so to me, that was a game changer. But I thought, okay, now we have data, we store data, but we don't know how to extract intelligence from data, and that will take more than my lifetime. So, I was not thinking that it would be so quick. And then in 2014, I was involved in a project where they were training systems to detect anomalies in CT scans, in medical imaging. And then I realized that on a task where humans are not naturally evolved, which is to interpret not natural but medical images, so where you have to train these physicians for many years, you could train a deep learning model and beat even the most experienced radiologist. And so that's where I realized, oh my God, this is happening in my lifetime. And so what is the right place to be part of this if you want to be involved? Well, you need to be in a place that has exposure to a variety of problem domains and has patience and has data, resources to make it happen. And slowly, one little step at a time, but we've been able to make a difference in several other products that our customers have been benefiting from.
Yeah, I like the characterization of areas that we're evolved to be good at versus those that we aren't. It's, as a classifier for problems that we should seek to apply machine learning for, it kind of reminds me of Andrew Ng's anything that takes us more than a second, but it's got maybe a more philosophical spin to it.
Well, more than philosophical, it's very easy to underestimate how difficult some tasks are. One anecdote I have is that with my students, I participated to the first 2 DARPA Grand Challenges. And it was very interesting to be in the audience and watching people who are not experts see this car drive by. And these cars really looked like they didn't know what they were doing. And so, how can you possibly not see that bush and drive over it when anybody can see the bush? It's obvious. People forget that if this is roughly the size of your brain, the size of your 2 hands, and roughly half of it processes visual information. So most of the real estate in your brain, even when you're absorbed in the most, in the most abstruse thinking, most of your brain is busy trying to make sense of the sensory data that comes through. So it's really a Herculean task. And on the contrary, some things that look very, very difficult to humans are trivial to computers. And so we've been able to make inroads in both. Some traditionally hard problems, like learning one from few shots, we have made progress thanks to also the evolution of deep learning over the past 5 years, as well as the evolution of hardware, optimization methods, and so on. But also, we've been able to better understand the problem, in a way which is independent of whether it's implemented with biological hardware or silicon hardware. There are some characteristics of learning problem that are absolutely fascinating that we've just started to poke into, and they are, from the perspective of somebody with academic inclination, is very fascinating to spend time thinking about.
Yeah. And we want to dig into one of those, and that is the work that you and your teams have been doing around this idea of Graceful AI. What I thought was most compelling about that is I think we've come to appreciate that when we're using machine learning models in production, we need to constantly evolve them, constantly train them to counteract the effects of data drift or drift in the distribution of our data. And your paper in this work in general kind of asks the question or prompts the question that, are there some negative effects associated with constantly retraining those models? What are they and how do we deal with them? I'd like to have you tell us a little bit about the broader motivation that led to this body of work.
Yeah, it's actually an interesting story because it's serendipitous, right? So, one of the luxuries of being at AWS is that you get exposed to a myriad of problems that you don't even know exist, and you would not dream of by just sitting in your office at the university. And so this was a case where, the natural mode of evolution of knowledge is continuous, like you mentioned. So we don't have this arbitrary separation between training and inference phases, which we do have in machine learning. But in machine learning, we have this phase where we train something, we build a model, we offer it to customer, people use it. At some point, either a better model comes along, and certainly if you follow the academic literature, every single conference, there's an incremental improvement, and you would like to harvest all these improvements so that can benefit customers downstream. But what we realized is that customers were not updating their models, and we were not understanding why wouldn't you change the model when this one performs better? Now, the definition of performance is the one that comes from academic benchmark, where we count the average number of errors, and we train to minimize a proxy of that, whether it's empirical cross entropy or some other loss, So, but basically the criterion that we as academic had guessed is most relevant is the average number of errors. Right. Turns out most people don't care for the average number of errors. They have very specific requirements for what type of cohorts they care about, and even specific subsets or subtypes of the data that particularly care about. And so we realized that the proxies that we were training for were not the right ones for the customers. They were just the ones that we, by default, had been using for years. But the conversation that triggered that was important, and it's an example of the customer-obsessed science, because we released a model that was better than everything we've done before. So we were very excited. And then we heard that customers were not happy. And so we were wondering, why is that? Well, because there is regression. What is the regression? Regression is when you have a new model, and that model, even though on average performs better than the old model, but it introduces mistakes that the previous model didn't make. Okay. And so even if these mistakes are fewer, when you notice the old model makes mistake that the new model makes mistakes that the old one did not make, you're puzzled as a user because how is this any better? And so and the conversation between a scientist and a program manager was around the tone. Well, of course, the new model can make a mistake that the old model didn't make. Let me explain something about machine learning to you. And the program manager would say, no, let me explain something to you.
About customers.
You're solving the wrong problem. And I was listening, I was thinking, okay, maybe we are solving the wrong problem. So this type of interaction with customer escalations is really a treasure trove for scientists, because every time there is an obstacle, for an engineer, it's a frustration because it's yet another problem to solve to get to the finish line. For the scientist, is an opportunity because there's something to be understood. And here, what was there to be understood is that we are really not optimizing the right proxy. And so that's where we started thinking about, why should the average error be, the right metric? Because some people care for, having sort of even performance across different cohorts of the data set, or some people care about having performance that behaves similarly in models that are deployed at the edge or at the cloud, and some people care to maintain compatibility with previous models because they built pre-processing, post-processing around the trained model, and so if you change the model, suddenly you break it, it is months of work, it's extremely expensive. And so we realized that there's a whole universe of problems that arise when you're trying to train a machine learning model, not just to perform well in terms of the average probability of error, but that performs well relative to the context of pre-processing algorithm, post-processing algorithm, pre-existing models that are deployed on different hardware, and so on and so forth. And so it's fascinating because this is a problem that I would have never thought about sitting at a university, and it would have not have occurred to us if it wasn't for a customer coming back and say, I don't like this, fix it. So that's kind of the essence of customer-obsessed science.
Yeah, there's so many interesting facets to this. One that jumps out at me is just how it's a reminder of how immature machine learning is. On the traditional engineering side, we've got this whole set of methodologies around testing, and one of those types of tests is regression testing. We know how to do that. Every engineering team worth its salt runs a series of regression tests before they release their product to make sure that the product isn't taking steps backwards, but this is new in the context of machine learning.
Exactly. And there's even some aspects of it which are very peculiar and specific to deep learning, or more in general, overcomplete models, for instance, for classification, where if you take a deep learning model, let's say ResNet 152, and you train it on a large data set, let's say ImageNet, if you repeat the experiment 100 times, retrain the same exact model on the same exact data, just from different initial conditions, okay, you converge to 100 different models, but all of them have exactly the same average error, let's say 87.3, okay, whatever it is. They all have the same average error. When you go and look, the mistakes they make, they're completely different. So it's as if they were trading mistake. I'll get this one right, but give me this one and I'll get it wrong. So it was really eye-opening because, wait a second. So they all make the same number of mistakes, but they're different mistakes. And this is when we realized that very often some of these criteria, for instance, equal error rate across different demographics, as well as compatibility with other models, are conflicting with average performance. But here we have a case, we have an ISO error rate surface where all models are equivalent in terms of error rate, but you can move along the surface in high-dimensional space to make sure that your model does not make or makes as few mistakes as possible that were not made at the previous model. So you can optimize criteria that are orthogonal and they're not conflicting with each other. So this was the first time we realized that, okay, this is yet another performance criteria that does not impinge on the existing one that we know and know how to optimize. So there are many fascinating phenomena that arise when you start observing the behavior of these networks beyond just very standard and well-established metrics.
A lot of work's been going into trying to understand how deep learning models work and understand their internals. Have you or other previous researchers looked at this idea of maybe the way that error rate, or not error rates, but the types of errors kind of cluster across this ISO error rate or accuracy frontier?
Yes, quite a bit of work. So, well, first of all, kind of a preamble. It's fascinating how 20 years ago we thought that with math and analysis we would be informing research in neuroscience, and now we find ourselves doing kind of artificial neuroscience and probing deep network the way neuroscientists probe neuronal networks, which is kind of interesting twist of events. But yes, we've been looking at that at various stages. So one is with a former postdoc of mine, his name is Hussein Mobahi. We were looking at universal adversarial perturbations, where we realized that if you take the data and perturb them in a way that hits the closest decision boundary, so that with the smallest possible perturbation, you change the class and you fool the network, so to speak, all of these perturbations are aligned, which is very mysterious. And then
aligned in what sense?
Say again.
Aligned in what sense?
They're aligned in the sense that their direction in the high-dimensional space of representations is parallel. They're parallel to each other. So that you can find a single perturbations that apply to all the data with high probability changes the class at the output. So that says something about the structure of the decision boundaries. There are regions of high curvature, and so it's very different from what we had in mind, kind of coming from standard low-dimensional classifiers like SVM and so on. There was another aspect that was really puzzling to me. So this was when Alessandro Achille, who's a scientist at AWS now, but when I was still a student with a friend from Harvard Neuroscience, they had this conjecture that neural networks exhibit critical learning periods. Now, what is critical learning period? So in biological systems, either you learn a skill when you're young or you don't learn. This is why you cannot teach old dog new tricks, and this is why if you're born with a defect like cataract or with severe myopia, unless you correct it early, no matter how much time you have to recoup, you never learn right? So the optical defect is fixed, so it's resolved, but your brain has not learned correctly, and then you never learn correctly. Yes? So, and this is normally attributed to biology, to biochemistry of the brain. You stop generating synapses, and so you age. But neural networks don't age. Their connectivity is fixed at the outset. It doesn't change. So I told him, this is, you guys are crazy. This is, why would you ever expect that a neural network would have a behavior like that? It turns out it does, and which is really puzzling because now now it cannot be biochemistry because an artificial neural network doesn't have any. There's a vague resemblance to the brain, but really this phenomenon must be an information phenomenon. And then we started digging to say, okay, what does even mean information in a deep network? A deep network is a deterministic system. So it has zero entropy. The weights are fixed, right? The input-output map, once trained, is deterministic, so it has infinite mutual information between the input and output. So all of the standard concepts of information theory are not useful, and they're not useful to probe the inside, the guts of the network. And so we spend a lot of time defining and measuring information quantities in these gigantic networks, hundreds of millions of parameters and now even trillions. And what we discovered, for instance, is that, I don't know if you remember the movie, The Eternal Sunshine of the Spotless Mind, where the protagonist has for whatever reason, wants to forget experience related to a person or a partner, and so goes to a company called Lacuna that does something, showing some pictures of the partner, zap the brain to erase memory of it. So we thought, well, maybe we can do that with deep networks, right? We can zap the brain to forget or to erase memory of something that you saw in your training set. And it turns out that that is possible to do with deep networks, because once you understand how information is defined and computed and distributed in the representation, then you can inject noise in very specific direction that will force you to erase a particular datum or a class or a cohort of data, which now is also important because of privacy issues and so on and so forth. So there's a lot of fascinating questions that arise when you try to understand how these deep networks operate, and you have existence proofs of what is possible to do thanks to biology, the human visual system, the animal visual system. So there is definitely a lot more back and forth between the biological inspiration and the analysis than there was 20 years ago, when we thought, that maybe we'll solve the brain, with analysis. And somebody in the 90s told me that, if you think of science and understanding as a process of compression, that, so you observe the astra and you could record their positions, but once you understand the laws of physics, you can compress them into a law. And maybe the brain is the most compressed possible representation of itself. There is no easier brain of representing the brain than the brain itself. And if it's true for deep networks, then how do we leverage? Our reductionist scientific method has not been successful in this particular area. So we need a more holistic approach. We need to define and measure information, and then once you do that, you realize that despite the gigantic dimension of these spaces, the amount of information that they store is a tiny fraction. And the way in which they store it is fascinating. I love it because I can claim that I'm still learning, even if I'm aging, because these networks at the beginning accrue a lot of information, sort of they memorize, and then they start shedding information, throwing away information. And they do this while improving the expected error or the test error in the data set that you have sequestered. So in a sense, it seems like forgetting or throwing away information is a necessary part of learning, which when I talk to biologists, they say, oh, of course, but I've never seen it written in math. I've never seen a claim that is defensible based on data arise from that. So it's really, there's a lot of interplay between understanding biological networks and understanding artificial networks.
Yeah, it seems like there would be, once you've established that, there are many, many levers that folks are using during the training process, the batch sizes and learning rates and cyclical learning rates, all of these things that if they're ultimately correlated to the rate at which the network learns and how things are forgotten, would be even more impactful than was originally believed.
Yes, that's a great point. One thing that we understood is the following. So all of these inductive biases that you mentioned, which could be in the class of functions with pooling, or could be in the optimization with SGD, with the choice of the batch size and the learning rate and so on and so forth, or they could be in explicit regularizer. So all of these processes are some type of regularization, meaning that these are added terms, whether explicit or implicit, to your training process, so that you don't just minimize the empirical error, otherwise you would overfit, but you optimize something that hopefully will allow you to generalize, and it can be computed using, for instance, pack-based bound, and now we know how to compute the information terms in the pack-based bound and so on and so forth. What we discover, however, is that normally you think of regularization as a process that smooths or regularizes your loss function. Mm-hmm. And this is not what's happening in deep learning. So there is a paper that we wrote with an intern at AWS at NeurIPS 2 years ago, which is titled Time Matters in Regularizing Deep Networks. And what it means is the following. So the intern, Aditya Golatkar, did the following experiment. He took standard regularizers that people use, for instance, weight decay and data augmentation. And then he had a few epochs of training without regularization, and then turn on regularization. So asymptotically, the loss function is regularized. The network would not behave at all. Vice versa. Turn on the regularizer, let the network converge for a few epochs, then turn off the regularizer. So the asymptotic loss is as irregular as if it never saw regularization. It only saw regularization during the initial transit. Yet generalization power is just as good as if you regularize all the way. So it appears that regularization does not affect the topology and the geometry of the loss function at convergence. So the asymptotics are really not that important. It's only the transient. Regularization affects what bottlenecks in the loss landscape you can manage to get into. And then critical learning period, which is what we were talking about earlier, tells you that once you get into one of these bottlenecks and onto a wide valley, and people talk about wide minima and so on and so forth, flat minima, it's very difficult to come back from that. So if you enter during the initial transit, enter the wrong valley, which you could do if you train with the wrong data, for instance, because your parents didn't realize that you were myopic, and so they didn't put your glasses on until you were 5, 6 years old. At that point, you cannot get back out from that valley, and you will never learn how to see correctly, right? And this is true for a variety of skills, for a variety of species, from songbirds to walking to deep neural network, which is puzzling and fascinating.
Yeah, the analogy that comes to mind for me, and I may be butchering my undergraduate materials science, but is one of annealing, where you can have two materials that are functionally equivalent by, structure, overall structure, but their internal structure is different because of the way that they've been created, via heating and cooling cycles and things like that. And it reminds me of a point that you made in the blog post, which is talking about model compression, which is, I think, illustrative of this entire conversation. The point was that in model compression, we often think of it as simply, trying to find a model with kind of equivalent error that is smaller or meets some other set of constraints, but the architecture, what I'm taking to be the structure of the models, matters a lot for the reasons that we've talked about. Can you elaborate a bit on that?
Yeah, so we have this concept that we call information plasticity, as analogous to neuronal plasticity. Neuronal plasticity is where neurons form synapses, form dendrites, and so they physically change configuration. In deep neural network, the configuration is fixed. However, what you notice when the network is trained is that some parameters don't matter at all, meaning that if you take that parameter and change it liberally, the input-output behavior does not change. So you could replace that parameter with noise, or you could replace it with zero. So this is called pruning, and observe no input-output changes in the input-output behavior. And so it appears, however, that during the initial transient, so you could say also that this parameter doesn't have any information, because you could store it with 0 bits and you will never know the difference. Vice versa, if you have a parameter, you change it a little bit, and all of a sudden the behavior changes, that has a lot of information, so you want to store it with a large number of bits. So, but it turns out that during the initial transient, the information counted as number of bits per weight moves around from the different layers, so it crosses and goes from upper layer to lower layers until it settles. Beyond a certain point, it cannot move. And so beyond a certain point, weights that are uninformative stay uninformative, even if you change the training set. And so that's really the structure of the network. So it appears that the effective connectivity, which is not the physical connectivity, because it's that's determined at the outset, but the effective connectivity as measured by the amount of information that connection carries, which we now know how to measure after several years of work. So that is very important. And if you knew that at the beginning, okay, you could train with a smaller network. The problem is that to get there, you need to go through this very high bump in information in the network, which needs the high dimensional space and needs a large number of parameters. And and there are, like you were suggesting, statistical physicists and physicists in general are very fascinated with some of these questions, because they have thought about high dimensional systems, including spin glasses and so on.
Mm-hmm, mm-hmm. So we've diverged pretty quickly from the specifics of the Graceful AI set of papers, but I want to return to those and dig in deeper. You talked about kind of how two models with the same accuracy can have very different types of errors, and how from a user perspective, that might be frustrating. They may get used to a certain type of error, and now the model changes, and all of a sudden the behavior that they're used to is different. And we want to, I guess in introducing this, you focused on the idea of regression, and meaning things that were working previously don't break. But are there kind of broader types of continuity that a customer might come to expect? And have you looked at that or to what degree have you looked at that?
Yes, we have. In fact, when we started this project, we thought it was a narrow set of use cases where, let's say, you have a photo collection, and now you update to the latest software, and which is, of course, much better than the one before, except that now you're searching for pictures of your cousin that you were able to find before, and now they don't show up in the search. You know what's going on. So that's the regression, right? So that you are frustrated as an individual user because something was working before and it's not working now. Something broke. So, but as soon as we came up with this, we discovered that there's a host of other related problems. For instance, we didn't realize that it is exactly the same problem as cross-model compatibility, where you have a service that runs on different platforms. Let's say it runs on the smartphone as well as on the cloud. And of course, on the cloud, you prioritize performance. You really have no constraint on how big the model is. But on your phone, you don't want to kill the battery in no time. And so you run a smaller model. So what do? Do you do the best you can do with the hardware you have on the phone, regardless of what the big model on the cloud does? Or do you try to train the model on the phone in a way that resembles or mimics the model in the cloud in a way that can be defined? And if you do that, then your trade space is not just the parameters for a chosen architecture. You also can optimize over the architecture. So now it becomes a hybrid search space over a continuous space of weights, as well as a discrete space of architectures. And so that we thought was a different problem, but it turns out to be exactly the same problem. Same thing with languages. We have services that build chatbots. And so the trained model sits at the center, but then customer build up on top of this model very elaborate post-processing workflows. And even changes that you would think are innocuous can break this post-processing. And you really don't know a priori what is and what is not doable. And so there is a whole space of dimensions along which you may want to impose either constraints or optimize together with the average error. And so, over the past years, we've seen dozens of cases across different applications at TWS where we see this problem arises. It's interesting that when we first published this paper, it was not reviewed positively because there's no comparison with anything. But yes, because this is not nobody has looked at this problem before. So it's really one of the most exciting times when you're not just having a new solution to an old problem, but you open up a new problem that on one hand is exciting for scientists to sink their teeth in. On the other, it can be beneficial because it can also help democratize the use of AI. Because right now, many customers are sitting by the sideline as new and improved models are coming by just because they don't want to face this issue of having to redo all the post-processing, pre-processing, and so on and so forth. Right. Let alone the cost of reprocessing large galleries, because if you have a photo collection, when I come in with a new model, you have to reprocess every single image in your gallery through the new model so that you can recreate an index to search. And also, if you have a few hundreds of thousands of images, that's okay. But if you have billions, okay, that starts becoming a little bit more complex.
And so it turns out that both the regression problem and the reprocessing problem are solved in the same way, and that is by utilizing the existing model. Can you talk more about the way you approach solving the problem?
Yeah, so the backward compatibility problem is fairly simple to formalize, and the solutions that we have proposed are very simple to implement.
And now the backward compatibility problem, the regression.
Yes, the backward compatibility problem is where you have an old model, you replace it with a new model, and you would like, as in the case, for instance, of your photo collection, to be able to use the old model to search old pictures without having to reprocess them through the new model. Okay. And so one way to do that is to optimize over a new backbone, a new model that has, bigger, larger number of parameters, different architecture, completely different, except that model is biased to use the classifier that the old model used. So in a sense, you force it to live in the same metric space where you can do clustering, where you can do search, and so on and so forth.
Yeah, just to interject, is that you might think that, okay, my typical practice might be to start with my old model and, freeze the weights on my classifier or something like that and just retrain and fine tune based on new data. is that inadequate to assure the kind of backward compatibility and the
So
errors?
you can do backward compatibility by just taking the same architecture and retraining it with the same classifier. Then you're fine. But if you follow the literature, every few months a new architecture comes by, and you want to harvest the benefits of that. And so in that case, these two representations that you fit to a classifier live in different spaces of different dimensions. So you cannot even compare them.
Yeah.
And so, but you can, however, force the network to develop a representation that is metrically compatible with the old classifier. So you can compute distances, compute angles, and so on. So that becomes a fairly cleanly formalized problem, and that you can, attack with standard methods of machine learning. Now, the positive congruent training, which is the training done in a way that minimizes the regression errors, that's a more amorphous problem, because depending on what type of errors you want to avoid, it may take different shapes. And something that is still puzzling us is that the current best performing model for positive congruent training is one that does not explicitly enforce that you make no mistake on a certain cohorts of data, but that is trained using ensembles which don't know anything about each other, and they don't know anything about the old model. So we call this future proofing, because training with this ensures that later there will be fewer of what we call negative flips. Negative flips are data points for which the decision
before and it doesn't
flips and becomes wrong. So there are definitely very open scientific questions that need to be understood. We just put there the first seed, but definitely there's a lot to be understood that we and others are working on actively.
And so what do these ensembles look like? What are the components of the ensembles?
The ensembles could be same architecture trained in different ways, or with different breakdown of the data, or completely different architectures. The only problem is that the ensemble is not viable, in practice, because if at inference time you want to run an ensemble of 10 models, your cost of inference will get multiplied by 10. And that's something that customers will not accept gladly, right? So we really need to figure out ways to perform positive congruent training at exactly the same cost as running one model, not an ensemble of models. So in a sense, it's a paragon of performance, because right now it achieves the best performance, but it's not a viable target for deployment, because it multiplies the cost by an integer multiple, and that's not, it's a non-starter. So, this is a science problem.
And so when you say that the ensembles can be, you didn't say anything, but that, there's you made it sound like the ensemble was not constructed in a particular way that had this property, but rather the act of using ensembles had kind of a regularization type of effect that addressed PCT.
Correct. And one would be induced in thinking that because ensembles work, then these negative flips are points that are very close to the decision boundary. So when you train different models, the boundary jitters around, and so these points flip. But in fact, we discovered that many of the data points that flip, are actually very far from the decision boundary. They are very high confidence data points. And so you're making high confidence mistakes, which are the worst kind, right? So it's not knowing that you don't know. It's a real problem. It's the Dunning-Kruger effect and all that. So.
And so what is the best practical approach to addressing this issue?
Yeah, so right now we have a form of what we call focal distillation. Distillation is where you train a model and then you train another model to mimic the input-output behavior of the first, but that model could be smaller or could have other characteristics. And of course, you don't want to imitate the old model, because then you would inherit also the mistakes. You want to imitate the old model only where the old model gets it right? And otherwise, you want to have the freedom to optimize according to the new architecture, better data, more balanced data, and whatnot. So,
and is there a difference between distillation broadly and student-teacher type of an approach?
Yeah, so it's a general umbrella of methods that go under the name of distillation or student-teacher models. Yes, and this is a particular class of them, where you don't just try to mimic the behavior of the model, but you try to mimic the behavior of the model restricted to the cohorts of data that interest you. Now, because typically this cohort of data, including the negative flips, is a tiny minority of the total. I mean, tiny could be in the order of 5, 6, 7%. So it is significant if you account for the fact that people fight very hard for a 1% performance improvement. And all of a sudden you squander 7% because of these negative flips. And so, but if you just do distillation on 7% of the data, that would be lost in the general loss function. So you have to do distillation in a clever way. Mm-hmm. That's what we call focal distillation. But it's an active area of research, and we both read about methods that are coming up that improve on that, and we also have internal efforts that are aimed at improving that.
Mm-hmm. It sounds coarsely like a composite of distillation and like active learning, where you're trying to identify the most important data to train the model on.
Yeah, that's an important point. We very strongly believe in active learning. We haven't quite been able to make it work the way we would like it to work. But there are so many open questions. We could we could spend the rest of the afternoon on this. But these are all very good.
And so you started with this was a problem that came up in the context of customer challenges. Have you is the solution in front of customers, or is this still at the research frontier and working its way towards practice?
It's both. So we are still working at the frontier, but some of our backward compatible training are now in the hands of customers. So typically, this is how it works at AWS. So once you have a solution, it gets deployed to customers very quickly. And there are customers that are also engaged in the process, so we can ensure that once we launch something, it has customer vetting and feedback.
Mm-hmm. One of the things that you mentioned early on in the conversation is, as well as in your blog post on the topic, is pointing out this idea of the artificial separate relationship between training and inference, and kind of speaking to how the brain is kind of online learning. Are you working in that area as well? And I'd love to kind of get your take on where we are as a community with regard to kind of breaking the artificial separation between training and learning.
Yeah, that's a great question. Yeah, that goes under the general umbrella of lifelong learning or continual learning. And typically in the literature, people focus on the problem of catastrophic forgetting, meaning that as you train with new tasks and new model, you forget other things. So how do you avoid that, and so on and so forth? There are big issues of scale that goes up, because as you train more and more tasks and more models, the question is, how do you fit them into an architecture? How do you grow organically the architecture, and so on and so forth? So there are a lot of very interesting questions. There's one piece of work that we recently did that gave us hope in this arena, which is a work on actually on language. Language is, there's always a small diatribe between language science team and vision science team, because language is quote unquote easy. Of course, it's not easy, right? But it's a domain that is very large but finite, and the type of nuisance variability to which language data are subject is very small compared to images. So when you have a sentence, you can move the words around, you can misspell them, and so on. But if you have an image of a cat, there's image of different cats under different pose, illumination, coat color, and so on and so forth. So there's infinitely many different embodiments of that concept. But in languages, both the data and the object of inference live in the same space. So, which is not true in vision. In vision, you want the label cat, but in the image, there's no, in the physical scene, there's no label cat. There's pixels. So we did this work in languages called TAN, which is basically it takes all language tasks. There's a variety. We took the most common, maybe a dozen or so, and co-reference resolution, A90T recognition, semantic role labeling, and so on and so forth. And Giovanni Paolini, who's a mathematician who joined our team a couple of years ago, was able to translate all of these different tasks into a single task, which is to translate between different augmented languages where the format of the language embodies the task. Okay, so by doing that, you have all these different tasks which you can keep training, but you're training one model. Okay, and then the format of the query or the format of the training data specifies whether you're looking for named entity recognition or some other task. And so in language, we're able to do that in a way that we haven't yet been able to do in vision. And still, it's only very early stages of multitask learning and continual learning, because we still have the pre-training phase, which is artificially separated, where you train a language model to predict missing words and so on. So I think it's very early. I think that area of investigation will go on for a while. And but definitely is an artificial separation, as you said, that is we need to do away with at some point. We're just not there yet.
And so I don't think I followed the connection between the format of the language and the lifelong learning aspect of that we were originally speaking to. Can you elaborate on that a bit?
Yeah, so right now, if you train for one task, the type of knowledge that you acquired is specific to that task, and you cannot transfer it to a new task which you learn. Because if you now take that model that you train on task one, now you fine tune on task two, you've lost something with respect to task one. Now you need to worry about not forgetting something about task one. So if you learn them serially, you have to face this problem of catastrophic forgetting. If you learn them simultaneously, it's also synergistic, because now there is knowledge which is shared across these tasks. So if you have small data set on task one, small data set on task two, you can train on the union of data sets. And for instance, if you have, Tolkien is an author and he lives in Moscow. Somewhere in the model, the information that Moscow is in Russia is there. And so if you ask the question, is Tolkien Russian? You may be induced and say yes. So, which you wouldn't if you had trained for each task individually. And then you don't need to worry about catastrophic forgetting. Quite the contrary, you can harvest synergistically information from different tasks.
Got it. Very good. What else? What else is your team excited about? What else are you focusing on? Or, speaking broadly about the field, what things that we haven't talked about are kind of on your mind?
Yeah. So, well, first of all, it's a very exciting time, because I don't think there's ever been a time, certainly not in my memory, but when you as a scientist have a chance to do things that impact people's life, right here, right now. Even if you were a scientist at the forefront of research through these waves that went through, like the semiconductor wave, the communication waves, the control waves, the wireless wave, the time it passed between ideation and realization was in the decades, right? But here, we have scientists who join after their PhD, and 6 months later, their code is in production. It's just unheard of. So it's very exciting because of that, and there's a lot of stuff happening. So the entropy is very high. I think where we start seeing a lot of excitement is where there is cross-task and cross-model learning. And right now we understand data, and now we finally also understand what information is. Information is in the data, but it's not the data, it's more. And now we don't quite yet what knowledge is, but knowledge has something to do with information, and we're just beginning to shed light on that. And hopefully at some point we'll be able to reason, not in the way in which we say we do reasoning in artificial systems, but really in ways that allows us to interact naturally with the environment and naturally with physical space, and naturally with machines, between human and machines. So.
Awesome.
And being AWS, again, is a little bit of a luxury in the sense that, when we joined, we had Mechanical Turk. Mechanical Turk was one of the culprits for the AI revolution. And there's A2I, which blends, artificial systems with humans. And so all the pieces are there, and it's up to the leadership of individuals to go and find the connections and make things happen, which is quite exciting.
Yeah. Well, Stefano, thanks so much for taking the time to join us and talk through some of what you're working on. Very, very interesting stuff, and enjoyed the conversation.
My pleasure. I enjoy as well. Thank you.
Thank you.